Okay, so this last one right here, let's get to that one, and we're almost done, I promise. All right, so another way you could ask it here says let B equals that, let A equals that. So look, they could ask you now this, instead of saying, is B a linear combination? Is B in the span? Is B, I forget the other way. But is B in the range of the linear transformation? So there's another way you could ask. And just all need to do the same thing, all right? So you're going to take B, you're going to put it over there as an augmentation, right? And then I'm going to go ahead and write the answer down here. You ref it. So when you ref it, you get this matrix here. You get 1, 0, 3, 0. The column over there, you get a 0. Then on the next one, you get 0, 1, 2, 0. And then a 0 again there. Then here we get 0, 0, 0, 1, and then another 0. And the last row is all zeros, but there's a 1 over the last row. So, yes or no? This is no solution, right? So it is not possible to take matrix A, multiply it by something, and get matrix B. It's not possible. So the answer to this is no. No, because I have a pivot in the last column.
Can we have like two column B answers? Like, could you find that somehow?
Say again?
If part B was 2 columns and just 1, could you have 2 things in your augmentation? And would you
could you do 2?
Yeah.
I mean, I guess, but I feel like that would be usually you're imagining it as a vector that you're trying to get, a place. So it's I guess you could check them both at the same time. But they would be separate. They would be separate from each other, I feel like.
It would be
I've never seen that.
It wouldn't be useful to do both.
Yeah, they would still maintain their own identity, kind of, I feel like.
Yeah.
Alright. Alright, so as you saw in the video, and then next section we're gonna do all these transformations, and there's all these little reflections and geometrical things, but this is one of them here. Alright, so I'm gonna have a little Schoology thing for you to do. But can you see what's happening like this transformation over here? You're going from here to here. So these dots are kind of the edges of a plane. So on your little video games or whatever, when they want something to get smaller all of a sudden, guess what? They do a matrix in there. They do a transformation matrix in their coding and stuff like that. Right? So do you see the transformation that everything is reducing in size? I don't know. Ask Miss Bergentil. She says use matrices on your algebra. Your what project? Oh, computer science? Yeah. All right. So you can tell what's happening here. It's basically reducing in size, right? And so you know how when you have ones along the column or along this diagonal, if you have ones, you stay the same. But when they're all 0.5, it's going to do what to your answer? It's going to shrink it by half, right? So basically what's happening here is this vector is turning into 0.5 and 0 and -2. You see what I'm saying? If you apply that transformation. This vector would turn into 0.5a, 0.5b, and 0.5c, right? Because it's multiplying. So if you multiply a times u and a times b, these would be your answers. All right, and you know what? We can just finish the. We'll just.
Nice class.
I mean, I could do it in 2 minutes, you guys. We just do it. Let's just do it, please. All right, just real quick. All right. So there are certain matrices. So this is one of them that do certain geometrical things. All right. So let's see what this one does. So if I have this matrix right here, this transformation matrix, let's take 0, 1, and 1, 0, and let's apply it to 5, 2. And by apply it, I mean multiply. Right? So what do you get when you multiply 0, 1, 1, 0, 5, 5, 2? What do you get? It's a 2 by 2 and a 2 by 1, so it's going to be a 2 by 1. So what's my answer for my top number? 2 and 5. It literally just flips it, it
That's a
switches it.
flipper. That's
Did you remember what that was in algebra, like when you switch the x and the y?
Inverse.
It was the inverse.
Get out of
And
here.
inverses are symmetrical over the lines y equals x, all right? So yes, this reflected it. But, you know, in olden days, you had x and y, and it was this line right here. So basically, you know, 5, 2 became 2, 5. So it was a reflection over that. But in what's it called, in linear algebra, we don't use x's and y's because we're going to run out of alphabet letters. So what they do instead is they use x1 and x2 when they're graphing something. So this is the line right here. This was the line y equals x. So this is the line x1 equals x2. So you would say, hey, these vectors are reflected about the line x1 equals x2. That's what that causes. It causes a reflection over the line x1 equals x2. All right, so let's do this one real quick. So first of all, so let's do 1, 2, and 0, 1 times, let's do 5, 2. So what happens to the 5, 2? So 1, 2 times 5, 2, what's that make? That makes 5 plus 4, 9. And the second one, 0, 1, it still stays 2. So it takes something that was over 5 and up 2, and it changes it into 9, 2. So like it pushes it that way. And I don't know if you remember on the video, when something's pushed that way, it's called a shear, a horizontal shear. So that's what that's going to be called. So next time, the whole section next time is all these different things. Reflection over a line, horizontal shear, vertical shear, blah, 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 reflection over the x-axis, right? But anyway, so they all basically deal with these little 2x2 matrices and like remembering what they are. But you can also just like do it and see what happens. Horizontal shear. Alright, so you're just figuring that out. And the last one down here is just a transformation preserves operation. Okay. So yeah, and so this transformation preserves the operations of vector addition and scalar multiplication, and the origin stays in place. So that's just a thing, like these things stay the same, and it makes addition and multiplication okay, and the origin has to stay in the origin. All right, that's it.